Now, in Bernoulli's equation, he didn't count the frictional loss in a fluid flow. So you see, in some situation, you can use directly by ignoring frictional loss of the fluid. You can use the Bernoulli's equation because frictional use in those cases very small. So you can simplification, you can neglect. But in reality, you have to count the frictional loss. For example, you are working in a city corporation and you have at least a 40 square mile of city. Now you need to distribute water throughout the city through underground pipeline. So in that case, you need to figure out how much will be loss. Then you need to figure out how much pump you needed. If there is no frictional loss, then what will be happen? You just get the water from the source and put in the pipeline. Then it will go all the way because our Bernoulli is saying that P by gamma, this term always constant. So if this term at a point is 1000, even your pipeline is zigzag or going over the hill, under the hill, right over here you have a pump. Still over here will be 1000 as per Bernoulli's equation. But in reality, it is not feasible. For example, you are delivering natural gas to the Dhaka city from Brahmanbaria or Koila. Then obviously, you need to figure out how much will be the loss in the pipe, frictional loss. And obviously, frictional loss will depend on the surface of the pipe and also nature of the fluid, mainly the viscosity of the fluid. If you have more fluid with high viscosity, then your frictional loss will be high. And we can show you by some equation. So how we can correct the Bernoulli's equation? So you see, this is a system, fluid system at point, I choose 2 point A and B. We are thinking length is L. So it might be 1 mile, might be 5 feet, might be 3 feet, depends. The pipe has a diameter and you see same amount of fluid going through the pipe. So Q is constant. And you look point A and B, they're in the same horizontal line. So in that case, potential height ZA and ZB is same, right? So if I apply Bernoulli's equation without loss, my equation will be this one. But actually there will be some loss. That loss we are saying HLF, that means hydraulic frictional loss. Now how we can figure out that loss? If simply you apply the Bernoulli's equation between 2 points A and B, then you will see that velocity at point B and A will be same. Why? Because Q equal to A1 or A area at point A into VA equal to area at point B into VB. But area in the both point is same, the way I draw it. So if you figure out that V equal to Q by A at point A, that will be giving you velocity at point A. Similarly, velocity at point B, Q by area at point B. But this area same. Q obviously is same. So in that case, you are getting VA equal to VB. So this term will be out, this will be out. And ZAB is same. So what will remain then? PA by gamma, PB by gamma plus hydraulic loss. So from this equation, if you figure out the hydraulic loss, you get this much. That means hydraulic loss equal to pressure difference between 2 points. Now, how can figure out the pressure difference? If you install a pressure gauge right over here, and you install a pressure gauge right over here, then you figure out the difference of pressure. Then you will get the hydraulic loss, right? But if 2 point is 1 mile far from each other, or might be 2 miles, then how will you get the reading? You have one option. You attach some electrical device. Say you are right over here, you are looking. Then you're looking in the monitor, right? That's why they do. Like you are working in a chemical industry, say fertilizer company. They have a lot of system, boiler, condenser. Then all the system you have to look through a monitor, right? So they have some sensor. This one after system installation, but you have to design the pipeline. So for example, this is 10 miles. You know the pipe diameter right over here from the design. You need to calculate the how much will be loss. Okay. So let's see how we can figure it out. We say this is the pressure difference between 2 points and location is known. Then we can calculate frictional loss in the pipe. In reality, frictional loss occur due to surface friction in the pipe, viscosity of the fluid, and also type of flow. So 3 factors it depends. Number 1 is viscosity, then type of flow. Is it laminar or is it turbulent? Then depends on the surface friction of pipe. So 3 factors, right? Surface friction of the pipe, viscosity of the flow, then flow criteria, either laminar or turbulent flow. So what happened actually right over here? Say total summation, if I say right over here, is 400. 100. Right over here, total summation 300, say 80. So how much frictional loss is 20. Okay. For example, you buy some candy for your younger brother or sister, say 500 candy, but fortunately your bag has a leak, and on the way it dropped you one by one. So 30 candy lost in the way. So that means your candy have now 470. So here is the 30. That 30 is the loss in the road, or we can say frictional loss in the pipe. Okay. Now, how we can calculate this frictional loss? So there is some scientists, they derive some equation. Number 1 is Hazen-Poiseuille's equation, then Darcy-Weisbach's equation, then we have Darcy friction factor. So normally in one semester I derived the Hazen-Poiseuille's equation, but due to the limitation of time, normally I give you the only formula and explain. Because I already told you before, the fluid mechanics class actually 2 class together. So we just discussing how we can figure out the frictional loss in a fluid flow in the pipe. We have 3 equations, Hazen-Poiseuille's and Darcy-Weisbach's equation. Then Darcy-Weisbach's equation, there is a factor, one constant he used, that one name is called Darcy friction factor. So but I told you that we can derive these 2 equations, but due to the time we will not derive these 2 equations. But I will give you the equation and explain it. If you are interested, you can derive. I will help you out. Okay. Now, so 2 things we need to know. These 3 formula. Then in the previous slide, I told you that friction factor depends on viscosity of the fluid. Also, flow is laminar or turbulent. Now, how we can figure out that a flow is laminar or turbulent without you observing? I think I have some slide now. That might be next lecture. So Reynolds number is a number. If you say fluid flowing in a rectangular duct in a air conditioning system, in that case, you can figure out the Reynolds number for the fluid. If fluid flowing through a pipe, you can figure out the Reynolds number. Based on the Reynolds number, you can say a flow is laminar or turbulent. So if flow is laminar, you need to use one equation. If flow is turbulent, then you need to use another equation. So that's why we need to know. So Reynolds number, we'll explain it later on more. But right now, just show you, this is called Reynolds number, rho Vd divided by mu. What is the rho? Density of the fluid. V, velocity of the fluid passing through the system. D is the diameter of the pipe, and mu is the viscosity. This is the Reynolds number. Now, if you have a circular, then you can easily figure out the diameter, right? But if you have a rectangular pipe or duct, how will get the diameter? So there is a other way we can figure out the equivalent diameter of the rectangular duct or rectangular pipe. So we'll explain you later on. So you see, we need to know this equation, Darcy-Weisbach's friction factor, then we need to know Reynolds number. Then we need to know it's a number. So when the flow will be laminar, when the flow will be turbulent, then we need to figure out the range of Reynolds number. The within, for example, within 1 to 10, flow laminar. Within 20 to 30, flow is turbulent. So let's say we'll explain it later on. Now, in the fluid system, you will see how many things we have. We have, sometimes we put turbine, right? We put pump. What pump does? It add energy to the fluid. It take electricity in the motor. Motor generate some mechanical energy. That mechanical energy you apply in the fluid. That means you applying some energy. For example, you might sitting in a room, your fan is running, right? So what happened over here? You giving some energy in the fluid. So he is kind of moving around. No electricity, fan is not moving, there is no airflow. Okay, so say a fluid entering at point A from the left side. So when he entering at point A, then you add a pump. So what will happen? Your energy of the fluid inside the pipe will be increased. Then he is leaving through point B. So point B, he will have some energy, right? And point A, he will have some energy. So when he came in point A, his amount of energy is this much, right? Then you add a pump. Now, how will figure out energy of the pump? If you buy a pump for your house or any purpose, if you look through the specification, you will say head of the pump. Head mean how much energy he can add to the fluid. More head, pump is more good. It will add more energy in the fluid. Okay. So when he came in at point A with this much energy, and when fluid entering at point A, then he will giving some energy, boost up, energy boosting, right? H pump. With that much energy, he is going to point B. So after coming point B, he has this much energy. Then he lost some energy between point A and B. So you get this one. Okay. So fluid pump, actually it adds some head to the fluid. For example, you coming in university for say from the home, you carry 120 candy. Now one of your friend give you 80. So your candy 200. So now you're going to the home, or you're moving from one building to another building. But somebody on the way, he steal from your back 20 candy. That means that is your frictional loss. So at point B, your energy will have 180. So that means your equation is 120. Originally you have. Then 80 candy somebody give you. That means you're getting from the pump, a total energy. With that energy, you're moving toward point B. But on the way, you lose 20 candy, frictional loss. So right over here, 180 energy is remain at point B. Okay. Now, what will happen? You have the pump, also you have turbine. What turbine does? It drink energy from the fluid, right? Turbine, it take the energy and produce the mechanical energy. For example, if you go in the Kaptai bath, you see hydraulic, the water right over here, height is rising, water is coming over here. Through this height, you make a channel and I put a turbine over here. right? It has some kind of blade. Okay. Now this height, potential height, is the fluid energy. Over here, velocity is 0. Then getting out through a small opening with higher velocity, then it hit the blade, it is rotating. That means, what does it mean? It taking energy from the fluid. So how we can write the equation in that case? So our pump, what it does is add energy to the fluid. So at point A, how much energy you will have of the fluid? This much energy. With this much energy, he entered at point A, just before point A. Now, point A, you have a pump. You have capacity of the pump is pump. You know, if you like to buy a pump, if you go to this pump store, they can tell you what is the head of the pump, like 20 meter, 30 meter, 40 meter. So more head mean it able to add more energy. So that's why we put over here H pump. And what is the unit of the H pump? Same as unit of the jet. P by gamma equal to what? You see, we learn that P by gamma, actually what is the unit is coming? P equal to H rho G, gamma equal to rho G. So ultimately what are we getting? Getting only H. Okay. So right over here, this much energy will have right over here in the fluid. Then he's moving toward point B. After point B, there is a turbine. So kind of he's energy eater. He is taking energy from the fluid and producing mechanical energy. So turbine also, how much energy he'll make from the mechanical energy, how much he will convert, that is called head of the turbine, H turbine. Then this much energy will leave fluid after the turbine, and there will be some loss in the road, right, in the pipeline. This will be HLF. And say energy from the fluid, it take 100. It cannot give you 100% mechanical energy from the turbine. There will be some loss. So even he is receiving energy 100, but he might produce about to 80 amount of 80% of energy, and least amount will be mechanical loss. Okay. So how you can interpret this thing? Say you start from your campus and going home. Okay. So you have 300 candy in your pocket. And if the gate, one of your best friend, he gives you 200. That means this 200 you are getting from the pump. Then you are going to the home. Same thing. You are sitting with a friend in a bus, and he's stealing every 5 minutes, like 2 candy or 1 candy. So on the way, he is eating 50 candy. Now, what is the turbine? Turbine also energy eater. So before you went home, and you found one more friend, he's extremely stubborn, and he's eating, say, 180. So how much now candy will have? So at point A, energy fluid coming with 200, that is this much energy, and pump is adding 300, 500, total 500. You are moving toward your home. So at the front of your gate, some of your friend taking 180, and how much will you have over here? That you need to figure out. Okay. So you count in the road, you lost 50. That means this is frictional head loss. This is ALF. And at the gate, your other friend, that means he's the turbine, he's taking 180. So total 230. So 230 plus 270. This much candy you can take it home. But that means when fluid leaving point B, you will have this much your energy in the fluid. Now you see turbine taking 180 amount of energy, but his efficiency is very less, right? For example, he don't know how to count 180. Instead of 180, he take 160. So rest 20 is the mechanical loss in the turbine. Okay. Now, how you will figure out the efficiency of the turbine and the efficiency of the pump? will not derive it because you learn it in the fluid machinery class. But we just give you a equation like efficiency of the pump. How to figure out efficiency of the pump? Pump add energy to the fluid, right? P out, right? He's giving energy to the fluid, and how much energy he's taking? He's taking energy from the motor, critical energy. So how will be the P out? P out will be H rho G Q. What is the H? H is the head of the pump, rho is the density of the fluid, and Q is the flow rate. That you put over here, you will get efficiency of the pump. That we put right over here. But in turbine is opposite because P input is this much coming in the bottom. This much energy he is taking from the fluid, and this much is the output. So your turbine efficiency will be P output by P input. And in case of turbine, if I say PT, turbine taking energy from the fluid equal to H turbine, that means head of the turbine into rho into G into Q. Q means flow rate, right? So far, any question from here? No question? Hello?
No, sir.
Okay, then we'll move on to the next lecture sheet. 1 second. Okay, did you able to see the new slide?
Yes, sir.
Okay. This is lecture sheet 9. Okay. Lecture sheet 8, 9, 10 is very important, not only for the exam. If you going to work as a mechanical engineer, that a basic requirement, like you figure out frictional loss in the pipe, you figure out what will be capacity of your pump. For example, you are working in a real estate company. Say they will make 10 building. Each will be 20-story building. There will be each floor. There will be 4 units. You need to figure out the size of the water tank. How much will be the rooftop? Say you figure out by considering amount of number of people, how much water they needed. Then they figure out capacity of the water tank, right? Then you need to figure out, you like to fill up the tank within 1 hour. Then what will be your capacity of your pump? What will be the frictional loss in the pump? Normally, for a household, what we do, we just go in the store, ask some mechanics, and they buy the pump. The mechanic will say, okay, buy 1 horsepower, 1.5 horsepower. Then it's okay, right? It's working. They're saying from their experience. But if you same pump you buy for a company, for a industry, then you need to have the calculation. Otherwise, you will violate the safety rule. For example, Rupur atomic power plant. There will be, you need a lot of water. You need might be some liquid fuel. You need to move from one place to another place. So then how will you figure out? You cannot just buy a pump based on your assumption, based on your guess. Okay, you can guess it, but still you need to show the your calculation. Okay. Say you are working in a very sensitive chemical industry, liquid oxygen, or they're making liquid nitrogen, or they are making some chemical for some power plant. In that case, obviously, you need to show the all calculation for certification purpose. Right over here, some question I put that might be come in the exam. So I'm not going through this question. You just read those questions, okay, and solve it. This one, the one time I give them assignment, just I put it over here, okay. And okay, now what is Darcy Weisbach's equation? What Darcy is saying, not Darcy, I'm sorry, Hazen-Poiseuille's equation. This one, Darcy is coming later on. This is Hazen-Poiseuille's equation. He's saying that if flow rate through a pipe is Q, and if we know the size of the pipe is D, and if we know the length of the pipe, where you like to figure out the head loss, say 1 mile or 2 mile, you know the L. Then by using this formula, the mu is the viscosity of the fluid. By using this formula, we can figure out the pressure difference between 2 points. More pressure difference, that means more loss. So what we're getting from here, you see delta P equal to Q into 128 mu L divided by pi d to the power 4, right? That you can figure out the pressure drop between 2 points without measuring, physically measuring. You don't need the pressure gauge right over here, okay? But this equation is valid only for laminar flow, laminar, incompressible, and Newtonian fluid. Also not valid for non-Newtonian fluid. So this is the limitation, this equation. If his flow is turbulent, you cannot use this equation. So this equation only you can use for laminar flow. But obviously in a lot of cases, we have found mostly the flow is turbulent. Then what equation you will use? So that limitation of Hazen-Poisson equation is overcome by another equation, is called Darcy-Weisbach's equation. Now I refresh your mind that what is laminar flow and turbulent flow, because Hazen-Poisson equation only applicable for laminar flow. So we need to know which equation we can apply in both situations, and what is the difference between laminar flow and turbulent flow. So already you know the definition, we discussed it before. So this is laminar flow, this is turbulent flow. Main difference, in laminar flow there is no transfer of momentum from one fluid particle to another fluid particle, but there is a transfer of momentum. Now what is Darcy-Weisbach's equation look like? So this is the Darcy-Weisbach's equation. They're showing with the dotted line, this one. What is LF? Frictional loss between 2 points, point A and B, equal to, here saying FL V average square divided by 2GD. What is the V average? I will explain it later on. So his use a friction factor, F, that is called Darcy friction factor. Then D, obviously diameter of the pipe. L is the length of the pipe between 2 points. Now, what is the V average? You see, if you look carefully, we figure out that V equal to Q by area. That is actually the average velocity. Why is the average, or is not the average? Means some velocity is higher than this value, some are lower than this value, right? So why it is saying that it is average value? Say there is a pipe, any point, if you figure out the velocity of the fluid particle at the wall of the pipe will be 0. At the center of the pipe will be high. Then gradually it will be reduced. So velocity profile, if you make a graph, it will be like that. That means a variable. But what we figure out, QIA, that means we are taking, you see velocity right over here 0, over here this much, over here this much, right over here this much. But what we do, we figure out a average velocity, just QIA. So that is the equation, HLF equal to FL V square by 2GD. And this equation you can apply for both laminar and for both turbulent flow, because this friction factor F, it depends on laminar flow or turbulent flow. Okay. Any question? Okay. So this is the Darcy-Weisbach's equation. Now he's saying that if flow is laminar, in that case, F will be friction factor will be 64 divided by Reynolds number in RE, or some book write down RE. Okay. So you see, if you know flow is laminar, you can directly use this formula. So what do you need? You need to know, figure out how to figure out the Reynolds number. then you need to know when, based on the Reynolds number, when flow will be laminar and flow will be turbulent. Now, for turbulent flow, he's saying F could be figured out from this big equation. Okay, and what is this equation? 1 by F in the left side, also 1 by F in the right side. This is Reynolds number, and this one is a factor ratio. What is the ratio? This epsilon is called roughness factor of the pipe or the wall surface, and D is the diameter of the pipe. So value or F also depends on the friction factor. If pipe is smooth like a glass, loss will be less. But if pipe is rough, friction factor will be high and loss will be high. Now, how will measure this epsilon value? Diameter of the pipe, you will get it. How will you get this one? Okay, that is surface roughness of the pipe. So normally in Bangladesh, what we'll do, you go to the store, buy a pump, right? But if you work a industry, multinational company or Western country, they'll not buy immediately. They will ask the manufacturer that what is the roughness factor of your pipe, or company might be show you in their website or in their specification. So obviously you will buy where surface roughness is very low, right? Otherwise your loss will be high. So all the company, they make the pipe, then they measure the roughness inside of the pipe. Obviously you might say this is smooth, right? Even the glass tube, if you look with the magnified view, you might see the surface is not the smooth like that. Okay, nothing 100% is not possible. Even you make a flat surface, say you have a glass on your tabletop and you touch with your hand, this is smooth and nice, this is 100% flat. But no, if you show a magnified some other equipment, you will measure, you will see your view is like that. That means still there have some surface roughness. So from this slide, what we learn that Darcy Weisbach's equation is good. This equation we can use for both laminar and turbulent flow. If flow is laminar, we can directly figure out the friction factor by using this graph. If flow is turbulent, then we can use this graph. Now, this equation. Okay, so this equation is very big. You cannot solve it. You can solve it numerically because F in the both sides, right, left side and right side, and there is a locked up. But there is some scientific calculator. I see a lot of students, they solve this, figure out the friction factor from this equation for turbulent flow. But you don't need to worry that much because how many variable over here? Reynolds number, surface roughness, and the friction factor. And there is a diagram. It's called Modi diagram. It is chart. In the Modi diagram, they plot this graph along three axes. That along horizontal axis, they put Reynolds number, RA. Along vertical direction, they put friction factor. Okay. And along this axis, they put this ratio, epsilon by D. And they generate some kind of graph. So if you know this value, Reynolds number, you know this one, then say you are this point and this point, you're coming right over here. From here, you're coming over here, you can figure out the friction factor. Okay, we'll show you how we can figure out. I by mistake or whatever, I put again the definition of turbulent flow. Now, you see that we need to figure out the when flow become turbulent, when flow become laminar. I already told you that it depends on the Reynolds number. Now, then you need to know how we'll figure out a Reynolds number, and you need to know the range. For example, you might say Reynolds number 10 to 20 flow is laminar, over 20 is turbulent. So what is the range? I just give you the example. The 20 is your critical point. So 20, instead of 20, it might be 200, it might be 2000, right? So before that, we need to know what is the Reynolds number. What does it mean? And how we can figure out Reynolds number for a fluid flow. Okay. So a while ago, I just told you that Reynolds number equal to rho VD divided by mu, right? This is the simplified form widely used, but As a fluid mechanics student, you need to know the definition and how it is come this short form. Okay. So Reynolds number is the ratio of frictional force. I'm sorry, inertia force to the viscous force. Viscous force means frictional force in the fluid is called Reynolds number. So you have to figure out ratio of two force. Number one is the ratio of inertia force divided by ratio of viscous force. Viscous force means force due to the viscosity. You remember the Newton law of viscosity, tau equal to mu dv by dy or du by dy, right? So if this is tau is a shear stress. You multiply by area, what you get? You get the frictional force at the bottom. And what is the inertia force? Inertia force equal to the acceleration, F equal to ma. Okay. So what is the Reynolds number? It is the ratio of inertia force to the viscous force of a fluid flow. So it normally expressed by RE, and some book you might see NR. Okay, or some book they represent it RN. What is the number? So this is the ratio. Reynolds number equal to inertia force divided by viscous force. Now, how will you figure out the inertia force? F into ma. Viscous force tau into area. Now, we'll put the unit and we simplify this ratio. How we can simplify? How will figure out a mass of a fluid? If you know the volume, multiply by density, you will get mass, right? So this is mass, m equal to density into volume. What is the volume? L cube. That we put over here. Now, what is the acceleration? Change of velocity certain time. That means v by t. So we put v by t at the top. Now, viscous force, tau into area. What is the tau? Tau equal to dv by dy. That means mu, we instead dv, we put v by L. What is the area? L square. We put L square. Now, we simplify this ratio. For example, you will have L. And this L, you have L square. Then you see there will be, now before you take it out, you need to do something else. At the top, you have rho L cube divided by V by T. This one we can simplify it more. We can write down rho L square L by T into V. What is my L by T? Distance divided by time. That is also velocity. So at the top, we are getting rho V square L square. That is right over here. Rho V square L square. And at the bottom, this square and this L out, rho VL. So you're getting rho VL in the bottom. Now you simplify it. Finally, you get this term. So Reynolds number equal to rho VL divided by mu. What is the L? It's called characteristic length. If fluid flow over a flat plate, in that case, we'll use the characteristic length. You like to Reynolds number right over here, your L will be this mass that we put over here. Now, but for a circular pipe flow or for a pipe, Reynolds number will be rho V D divided by mu. Instead of L, they use D. Now, rho V D by mu if pipe is circular. But a lot of time you might see there is a flow, but pipe is not circular. For example, if you go a very commercial building, they use air conditioning, rectangular duct. In that case, your pipe area is rectangle. How will you use the Reynolds number? So instead of only D, they're saying use DH. DH means hydraulic diameter instead of diameter. So if you know the hydraulic diameter, how can you figure out the hydraulic diameter? Then you can figure out the hydraulic diameter for rectangular cross section. For example, you have triangular cross-section pipe. How will you use the Reynolds number? In that case, you figure out equivalent diameter, that is kind of hydraulic diameter. Then you put in this equation. Then you get the Reynolds number. Now, how will you figure out the Reynolds number? Rho V, rho is the density, V is the velocity of the fluid, mu is the viscosity. So you just need to figure out the hydraulic diameter. Hydraulic diameter equal to 4 into cross-sectional area divided by weighted perimeter. So you need to know what is weighted perimeter. For example, this is, I'm saying, full square duct. So how much will be the area of this area? If length is L, area will be L square. So I like to figure out hydraulic diameter of this square duct. So 4 into cross-sectional area. So 4 into L square, right? Divided by weighted perimeter. Weighted mean if fluid flow, full flow, then this mass will be weighted perimeter, like kind of Bangla visa length. So your weighted perimeter will be 4 into L, right? So ultimately you are getting only L. Now, instead of square, say you have a duct rectangular. This is A and bigger length is B. How to figure the hydraulic diameter? So hydraulic diameter in this case, dA is equal to 4 into cross-sectional area. What will be area? Length into width, 4AB. What is the weighted perimeter? Weighted perimeter, 2A, 2B, right? This is also A, this is also B. So there will be 2A plus 2B. This will be hydraulic diameter of a rectangular cross-section. Similarly, if you have a circular pipe, I will figure the hydraulic diameter. So D equal to 4 into cross-sectional area. What is the area? Pi by, or I can say pi by 4 square, right? If there is a full flow, what is the weighted perimeter? Perimeter of the, that means weighted length. This whole inner surface will be weighted, right? So this length will be 2 pi r. 2 pi r. This one we can write down pi d. So I just write down pi d. So how to getting actually this 4 out, this pi out. So the square with d out, we getting only diameter of the pipe. Okay. Similarly, if you have triangular pipe, so you need to figure out hydraulic diameter 4 into cross-sectional area. You'll figure out what kind of triangle, figure out the area, right? If this is B, height is S, you can say area equal to 1 by 2 half into base into height. And what will be the weighted length? If this segment length is A, this is C, then your weighted length will be A plus B plus C. Okay? Easy, just you need to remember this formula. 4 into cross-sectional area divided by weighted perimeter. If you have hydraulic diameter, that hydraulic diameter you put it over here. How will you get the V? V equal to QI area. Now you need to know the ranges, when it will be a laminar and when it will be a turbulent flow. So Reynolds number, if we found less than 2300, then flow is laminar. For example, right over here. If higher than 4000, flow is called turbulent flow. And in between 2300 to 4000, that is called transitional. That means, say you have flow 2500, what does it mean? That means flow is not completely laminar, also is not completely turbulence, it's converting from laminar to turbulent. Okay, so you need to remember this range, that even you go for job interview, sometimes they ask what is the critical errors number, and they can ask you how will figure out a flow is laminar or turbulent. Write down the equation. Sometimes they ask what is the hydraulic diameter, how will figure out the hydraulic diameter of a square duct or of a rectangular duct. Okay, so remember over here, if is Reynolds number less than 2300, flow will be laminar, and higher than 4000, then flow will be turbulent. Okay. This one we already discussed it. There is a pump over here. Fluid is leaving. Then what will be the energy of the fluid right after the point B? So this much energy of the fluid at point A, and pump energy added to the fluid S pump. With these two energy, fluid is heading toward point B. but on the road there will be frictional loss. This much energy is remaining in the fluid. Just refresh your mind again. Similarly, if you have a pump and turbine both in the system, then how we can figure out, write down the Bernoulli's equation. So right over here we have a pump. So before point A, energy of the fluid is this mass coming entering to the pump, and pump is adding some energy. So with this much energy, the fluid is heading toward point B, and he's leaving right over here. So he's leaving with this much energy, and HLF is the frictional loss in the pipe. Then he generates some turbine taking energy, H turbine, head of the turbine, from the fluid. And rest, because turbine efficiency, nothing has 100% efficiency, there will be some loss. If he take 100 meter of head, turbine head, and after you convert mechanical energy, you might get 80% or 90%, 10% might be mechanical loss. That loss is right over here. So you see this much, the red color, energy absorbed by the turbine, this much energy remain in the fluid, leaving point B, HL frictional loss. And this much energy in the fluid just entering to the pump. And H pump, this much energy is adding by the pump to the fluid. Now, the summary of all formula, that how we can figure out the power of the pump, power of the turbine, and also we figure out the efficiency. So you see fluid power, always you have this equation, rho G Q H, and pump, H pump, that means the power of the pump equal to rho G Q H pump. Turbine, rho G Q H turbine. Now you can check the unit, that actually rho G Q H, is it giving actually power? You can check. What is the unit of rho? Kg meter cube. Unit of G, meter second square. Unit of Q, meter cube by second. Unit of H in meter. Now if you simplify, you will see this meter cube will be out. So you have kg meter second square, that I put over here. Kg meter second square right over here, and you have meter by second, right? That meter by second over here, and kg meter per second square equal to Newton. So you got Newton meter per second, and Newton meter equal to joule. So joule per second equal to watt. Okay. Now how we figure out the efficiency of the turbine? This is efficiency of the pump, and turbine is this one. Okay. Frictional Darcy-Weisbach equation, HLF equal to FL V average square divided by 2 G D. And any pressure drop, if you know the HLF, you can figure out the pressure drop. Pressure drop equal to rho G into HLF. Okay, now we can solve a problem. You see right over here, kind of a pump. Right over here is a pump. Say water coming from river or some other source, entering the pipe at point 1. And right over here, diameter of the pipe is given 230 millimeter. And you add a pump, then is going through a certain height, Z2. They are not saying how much the Z2. Then leaving the water through the outlet. And right over here, the diameter of the pipe is 100 millimeter, the material reduced, right? And this is the pump. Now, you see these 2 points, they add a manometer. And in the manometer, they're saying fluid is mercury, Hg. And you see right over here, manometric deflection is given, 3 meter. So let's see what they like to know. It's saying water flowing at the rate 0.5 meter cube per second. That means this value is given, this one, actually Q, as shown in the figure below. Find power requirement by the pump. That means you need to figure out P pump, power of the pump. That means what capacity or watt or horsepower of the pump. Assume frictional loss in the pipe is 3.22 meter. Frictional loss from here to here. So HLF is given. So it's good that you do not to use that Weisbach's equation over here because they are already given. Now, how to figure out the power of the pump? What is the formula? Power of the pump P equal to rho G Q into H pump. So if you know head of the pump, you can figure out the pump power. Now, how will get the head of the pump? Now you see Q is given. We can apply Bernoulli's equation between point 1 and 2. Then what will get from 1 and 2? You get 0.1 P1 by gamma. 1 second, let me erase all the way. Okay, I like to apply the Bernoulli's equation between point 1 and 2. First apply point 1. Then you get P1 by gamma plus V1 square by 2G. If you think this is the reference line, then height of point 1, that means Z1. Z1, this much energy in the point 1. Then you add a pump, right? That means how much energy adding to the fluid by the pump? That will be equal to H pump. This H pump we need to figure out. Okay, so this much energy heading toward point 2. So point 2, how much energy of right over here? That will be P2 by gamma plus V2 square by 2G plus Z2 plus loss in the pipe on the road. Now how we figure out the V2 and V1? You see Q is given. We know V equal to Q by A. So easily we can figure out V1 and V2. So V1, V2 you know, right? HLF you know. Z1, Z2 there is given, you can figure out Z1, Z2. V we know. So H pump is function of P1 by gamma and P2 by gamma. That means if you take H pump in the left side, there will be P2 minus P1 divided by gamma. So that means you need to figure out a pressure difference between 2 points. How will you figure out the pressure difference? By the manometry. So let's say we can solve it, that how you can use the Bernoulli's equation with frictional head loss. Let's see. Did you see the MathCAD file? Hello?
Yes, sir.
Okay. So at first you draw the figure. This is our datum, that means reference line. Then figure out what is how many data is given. Density of water 1000 kg meter cube. In the manometric fluid mercury, Hg mentioned, this manometric fluid has a specific gravity of mercury 13.56. That means it is 13.56 times heavier than the water. So rho m will be 13.56 into rho w. That means density of water. So rho m equal to this mass. We're getting. Then deflection in the manometer 3 meter is given already. Diameter at 0.1 you convert in meter 0.3, 0.23, and diameter at 0.2, 0.18. So diameter write down, or Q is given in the problem. Frictional head loss is given this mass 3.22 meter. Then power of the pump, that you need to figure out. Power of the pump equal to rho G Q H pump, right? Now, if I make a copy of this figure, okay, we can check it right over here. So we'll apply Bernoulli's equation between point 1 and 2. So first apply point 1. So P1 by gamma, this part, P1 by gamma. V1 square by 2G plus Z1. Obviously Z1 will be 0 because this is the head. I'm sorry, data reference line. Then H pump, this much energy pump adding to the fluid. At point 2, this much energy with this much energy, fluid leaving point 2, getting out from the point 2. And how much is lost in the way? Frictional head loss, HLF. So HLF is given. Z2 is not given. Z1, 0. Then V1, V2 is not given. P1, P2 is not given. But we know that Q is given. But we know that Q equal to AB. Then I can say A1 into V1 equal to A2 into V2 to V2. So you can easily figure out the A1, V1. V1 will be Q by A1, V2 will be Q by A2. So this is our Bernoulli's equation. Then we are saying Z1 equal to 0. Z2 we don't know. We just keep it equal to Z2. V1 we don't know. V2 we don't know. P1, P2 we don't know. Okay. So if we know the H pump, that means head of the pump, H pump from here, then we can figure out the power of the pump, because power of the pump P equal to rho times G times H pump. I just put HP into Q. So H pump we need to figure out. So in the equation you see there is H pump. So H pump equal to P2 by gamma W minus this term P1 by gamma W, then this velocity term, right? Velocity we can figure out from this equation. But now how we'll figure out this difference? This one we can write down P2 minus P1 divided by gamma W, right? So this one we can easily figure out by applying manometry in this point and this point. Okay, so let's see how we can figure out the manometry. If we think this is we apply right over here and right over here, both pressure will be same, right? Because they are in the same height of the manometry fluid. So at first we take the left side. You take the left side, then we come from point 1. What is the pressure at point 1? Obviously P1, right? Then you are coming down until this point. Coming down how much? Vertical height. If you check carefully, your vertical height will be this much. If I make a line over here, this much, right? Through water. This much you are coming down, right? This point. That means P1, you coming down. Then what will happen? Plus, as per manometry. So plus, 1 second. Plus, then height is, bottom height is Z, H rho G. So Z times rho. What is my rho over here? Water into G. So you are coming right over here. Now you need to come from here to here. That means manometric height, right? So if I say that one is H, not only you put the H, or I can say HM. HM equal to 3, right? Into rho. What rho will be over here? Obviously this will be manometric height. So you need to put rho M into G. Rho M into G. So this mass pressure you are getting left side. Now you figure out the pressure at the right side, and both will be the same value, right? So equal to, you start from point 2 all the way coming down. So pressure at point 2 equal to P2. You are coming down, then it is plus. What is the height? You are coming down this point. So your height Z2 plus Z plus this 3. And all the fluid is water. So from here I can say this is Z2 plus Z plus 3 meter. This 3 meter we designated by ASM, right? Then star, what will be rho over here? Obviously this will be rho of water. So rho of water into G. This one will. Same thing we did over here. Instead of ASM, I just put H over here. Okay. Then you simplify. From here you figure out P1 minus P2 minus P1. That means you need to figure out this value. P2 minus P1 divided by gamma W. So after you simplify from this equation, and you will see this equation, the value of the Z will be out because Z is in the both side. This Z is out. Okay. So you see the H gamma M, right side, Z2 gamma W minus H gamma W, right? Now both side you divided by gamma W. Why? Because in our this equation, it is P2 minus P1 divided by gamma W. So right over here, this term will be out. Z gamma W, Z gamma W. Both side divided by gamma W. So you are getting you see right over here divided by gamma W. So H gamma M divided by gamma W. Z2 by gamma W, gamma W, gamma W out. H gamma W divided by gamma W, gamma W out. So you have only this term, right? Now this value, that means this is, if I say I take H common between this term and this term. So we have this term minus Z2. Now this value, if we put in equation 1 right over here, I will write down over here. This is P2 minus P1 by gamma. This value is already given. You see this Z2 will be out. So from these two equation, finally you are getting this term. Okay, I'd like to bring it down. So this term you are getting. Now I will get the V1 V2. HLF is given 3.22. V1 V2 Q by A. Gamma M, that means the Pacific ratio of Pacific gravity of this is Pacific gravity actually. Gamma M divided by gamma W. Pacific gravity of water 1 and total Pacific gravity of mercury 13.56. So at first you figure out the area at point 1, I by 4 d1 square. Area at point 2. So you get V1, you get the V2. Now then you figure out the gamma M and gamma W. Then you put all the value in this equation. Then you will get the H pump. So H pump, we are getting 42 meter. I'll get the power of the pump, rho G Q H pump. So just put all the value over here. You get the power of the pump. Then you can convert in kilowatt. Okay. So far, any question? No? Anyone? Any question? Okay. We have 9 minutes, 9 more minutes, so we can solve the next problem. Okay. It will be quick. Okay. Let's solve the next problem. Problem number 2. Okay, this one. You see, this is kind of dam. Okay, water is coming from the left side, and height of the water is increasing. Total height is 70 meters. And then there is a turbine. So what turbine does? It take energy from the fluid and produce mechanical energy. So turbine producing some energy right over here. Then the fluid going through the nozzle of the turbine right over here with certain velocity. So you see from here the height of the point 1 is given. Height of the point 1 is 70 meter. And height of point 3 from, if this they are saying this is data, you can take data anywhere. If you take data over here, then height of the point 3 is 20 meter. And now there is one thing, if you see, this nozzle is making 45 degree. This is the nozzle and this is the horizontal line. So with this horizontal line, this nozzle making 45 degree angle. This angle 45 degree. Now when fluid coming out through the nozzle, you see right over here velocity is not given, but water is getting out like that. So, but right over here, the tangential velocity is given at 0.4 is 15 meter per second. And you see the marking in 0.3, then you say D equal to 50 millimeter. That means that is diameter of the nozzle at 0.3. Now you see what they're saying. Water flowing from a turbine as shown in the figure below. Find the power developed by the turbine. If turbine efficiency is 80% and frictional loss in the pipe is 5 meter. So you need to figure out the turbine efficiency. What is the formula? This is the formula. P output divided by P input. P input, that means energy from the fluid. Rho G Q H turbine. And efficiency is given over here 80%. So you need to figure out the P out. And frictional loss is also given in the problem. So how we can figure out the H pump, H turbine. So you see at 0.1, if we apply Bernoulli's equation, P1 by gamma plus V1 square by 2G plus Z1. With this much energy at the 0.1, then fluid coming down through the turbine going at 0.3. So if I apply the Bernoulli's equation between 0.1 and 3, then what are we getting? This much energy 0.1, then is going through the turbine. And from the turbine, you are getting some energy. Turbine receive energy or drink energy from the fluid. So how much energy will drink? H turbine, head of the turbine, plus fluid getting out from 0.3. How much the energy? P3 divided by gamma plus V3 square divided by 2G plus Z3. With this much energy, fluid is getting out through 0.3 and it is HT. Then how much the loss HALF? So loss is given 5 meter, right? Now you look carefully how much the pressure at 0.1 and how much the pressure at 0.3. Both are atmospheric pressure. So P1, P3 will be out. How much the velocity at 0.1? If maintaining constant height, V1 is 0. So only left side we have Z1. HT V3 by 2G. Z1 is 70 meter, Z3 20 meter. So HLF is given. So I'm crossing this one. So what is my unknown over here? Only B3. So if you are able to figure out the B3, then we can figure out the turbine output part easily. Okay. So let's see how we can solve it. Okay, anytime problem given, at first you need to figure out what are the data given. You draw the figure, then you figure out the data. Okay, you need density P by gamma, right? We obviously saying water. So you say density of the water rho equal to 1000 kg meter cube. HLF given in the problem 5 meter. Diameter of the nozzle at 0.3. Given 50 millimeter, that means 0.05 meter. Efficiency of the turbine given 80%, that means 0.8. At V4, you see horizontal velocity is given 15 meter per second. And angle of the nozzle given theta n 45. What you need to figure out? Turbine power. Okay. Now, this is the side note. I just put it to explain so you can understand easily. Okay. So you see right over here, this is P turbine, rho G Q turbine. This is input. And efficiency of turbine is given. So P in equal to rho G Q turbine, you can figure out P out from there easily. Okay. Now, what is the challenge over here? If I draw the nozzle, say this nozzle, fluid coming out going this direction, right? Right over here, velocity is B, horizontal velocity, 15 meter per second. So what will be velocity right over here? I will figure out. You see, right over here, angle 45. So I'm saying velocity over here, V. So what will be horizontal component of the velocity? V cos 45, right? And what will be the vertical component? V sin 45. And that means this fluid somebody pulling with two force on the horizontal direction and upward direction. That's why flowing this direction, going upward. Now he gradually moving upward, but gravitational force pulling him downward. This force when become zero, then coming right over here, this vertical component forces become zero. Then you will have only the horizontal component, not the vertical component. So that means this velocity 15 meter per second equal to v cos 45 equal to this 15. Okay. Now coming over here, then what will happen? The g gravitational force working downward, horizontal component following toward the right, then is fluid is coming right over and come down ultimately in the ground. So I mentioned it right over here that
Sir, we have class from 10:30.
10:30. Okay.
Sir, it's already ended.
Only this slide. Should we complete? 2 minutes.
Yes, sir. Please
Okay,
proceed, sir.
that's 2 minutes. Okay, thank you. So you see, v cos v3 cos 45, that will be equal to v4. So from here we can figure out the v3. Okay. Now we are applying the Bernoulli's equation. Now v3 is there. We need to figure out the turbine power. So we need the Q. How we get the Q? V3 is given. You figure out right over here. You multiply by the area, you get the Q. So V3 is over here, then Q equal to A3 into V3. So this is the Q. Now you apply Bernoulli's equation between point 1 and 3. If you apply Bernoulli's equation between point 1 and 3, then see what you are getting over here. P1 by gamma, B1 square by 2G, Z1, then H turbine, then frictional loss, this much energy leaving from point 3. Z1 70 is given, B1 0, P1 equal to atmospheric pressure, P3 atmospheric pressure, B3 we already figure out, Z3 20 meter right over here. So after putting all the value, you get the head of the turbine. If you have head of the turbine, then use this equation, efficiency. Efficiency is 80%, rho g Q turbine, then you figure out the P out. Okay. So